Then we continue with our introduction to probability theory. And so what we covered last time was, so the topic is still probability theory. And of course we're doing this, before I forget to put it into context, the reason why we are doing this and why we are talking about it is because we're interested in formulating the general linear model. And the main reason why we're talking about probability theory is because we want to know what this epsilon is. So basically, with respect to our model of interest, not much has happened yet. We're still just trying to understand its formulation. Now, for probability theory, what we did last time was random variables and joint distributions. And keep in mind that what I'm doing here is fairly intuitive. So if you look into math books on probability theory, of course, this will be much more formal, but it's also the kind of applied probability theory coverage that you will find in books that call themselves machine learning books. So that is what we did last time. One more thing we also looked at last time was marginal distributions. So that was basically when we looked at our two random variable joint distribution and we computed marginal distributions. And then, so basically we did that, and that, and we had more things on our list. And the first thing that we'll also deal with today are conditional distributions, mainly because we need the notion of independent random variables. So that's actually where I want to get to with this whole thing. And while we're at conditional distributions, and because you sometimes will come across it, we will talk about Bayes' theorem. And once we made it to independent random variables, then I think it's time to talk about Gaussian distributions. So that's still the outline. Covered a bit last time, but we will have to do more. Are there questions concerning random variables, joint distribution, marginal distributions that you feel we should answer before we go on? Nobody remembers last Monday anyway, because there was this FMI workshop on the weekend, which erased everything. Okay, doesn't seem to be the case, so then let's talk about conditional distributions. And actually we will start that by going back to a joint distribution. So the topic is now conditional probability or conditional probability distribution. Conditional probability. And I assume that you, all of you, have heard some stuff on conditional probability before. So maybe you've seen this goat problem. Who is familiar with the goat problem? This thing that there are 3 doors and behind each door there's a zonk. That was in the 90s in Germany. But does anyone know this goat problem? With the 2 doors, and you have to choose one, and then you can switch or you not switch, and then you can calculate whether it's better to switch or not switch. You don't know this? Huh. That's more like general knowledge for quiz shows than something we will do here. But that's kind of something that is often used in also to introduce conditional probability. We will use a different way. I just wanted to, but who has heard about conditional probability? So please raise your hand if you have heard about conditional probability. The psychologists, there was no conditional probability. Bedingte Wahrscheinlichkeit. No. Okay. Anyway, then there's something completely new. I thought that it was taught in psychology or statistics. Anyway, then that will be completely new for some. But we will start again where we left off last week. So we had something like that we called random variables, which could take on values. And I'm again doing this by example now here. So we came up with a joint distribution over two random variables by just defining it. We wrote down probabilities for x taking on the value 1 and y taking on the value 1. Yeah, good. And x taking on the value 1 and y taking on the value 2, and x taking on the value 1 and y taking on the value 3. So that's all possibilities that exist if x takes on the value 1. And then there are more possibilities, namely if x takes on the value 2. And so we made a table like that where we defined the joint distribution, and now I left a little space, but we will be able to manage. So let's say we define this. Actually, last week I always wrote equal, but really it's definitions, but then it's a little bit also of overkill of definition signs. So let's define this as 0 over 6. And this define this as 1 over 6, and define this as 2 over 6. So we have 3 over 6 left, and then let's say this is 1 over 6, 1 over 6, and 1 over 6. So now we did the same thing that we did last time. So we distributed a probability mass of 1 over all these cases, and then we talked about that how you can think of it from a sampling perspective. For example, that's what we did last week, that you would expect if you now take samples from this distribution and look at the outcomes for x and y, and are particularly interested in the outcome x equals 1 and y equals 1, you would assume that you never get a sample like that, because the probability that this happens is actually 0. And then what we did is also to look at the marginal distributions. So we looked at, for example, the marginal distribution of y. So that was the probability that y takes on, looks like a j, that y takes on the value 1 over all possible cases that x might take on, and that probability is what?
1 over 6.
There you go. And while you're at it, continue. What's the probability that y takes on the value 2?
2 over 6.
And the last one?
3 over 6.
And then we have the other marginal distribution. So the probability that x takes on the value. Sorry, yeah, thank you. Like that. And then we have the marginal probability that x takes on the value 1, regardless of the value of y. That is what? 0?
No.
Y 0 over 6? No, not quite 0 over 6, but why do you think 0 over 6?
Well, 0 over 6 plus 1 over 6 plus
2. And that's 3. 3 over 6. Yeah. That's what you mean. Okay. But you said 0 anyway. Good. That's 3 over 6. And actually we can already, because we know the marginal distributions are normalized, we can infer that then p x equals 2, also the probability of 3 over 6, but we can also check that. And we cancel that. And we again see that this is 3 over 6. Good, so that is where we left off last week, and now we are interested in the notion of conditional probability. And the way I introduced that here is in the following. So we have defined with this distribution over two random variables a joint distribution. I also call distributions in general, but joint distributions in particular, I call them probabilistic models. So we have defined a probabilistic model, which is here fairly straightforward. Of course, the GLM is also a probabilistic model, and there are many more probabilistic models, and they are defined in different ways sometimes. But what is the same thing for all probabilistic models is that they define probability distributions, and in the Bayesian case, and often joint distributions. Now, in probabilistic models, one is also interested in conditional probabilities. That is the probability distribution of a random variable given that the other random variable takes on a specific value. So let's first maybe think about the distribution of y if x is 1. Yeah. So we are now interested in the case that x is 1, and we are interested in the probability distribution over y. This is often written like this. So py given x equals 1. And if you see something like this, you should always, again, think of the fact that y can take on different values. So in fact, what is meant by this kind of short statement is the thing that y equals 1 given x equals 1, py equals 2 given x equals 1, and py equals 3 given x equals 1. So this vertical bar here, so this thing, this is read as given as. So that's basically just some notation about conditional probabilities. So we are interested in the conditional probability distribution over the random variable y, given that x equals 1. And I haven't told you what that is yet, but I think if you look at the first row of our probabilistic model, you should have a fairly good intuition of what's going on with the probability distribution of y if x equals 1. So you see that x equals 1 in all these cases. So now let's say x equals 1, and you're supposed to tell me the probability that y equals 1 given that x equals 1. What would you say?
0.
0. Why?
Because in the first deterministic question it says when x is 1, y is 1, that's probability of 0 6.
Yeah. So the probability of the joint occurrence of x being 1 and y being 1 is 0. So that if you know that x equals 1, then you know, and you're interested in the case that y equals 1, then you know, then you know that this basically can't happen. The other question one can pose based on the joint distribution: if x equals 1, what is more probable, that y equals 2 or y equals 3? Why? Yeah. Yeah. Good. So basically what I'm trying to demonstrate here is that from looking at a joint probability distribution, you basically know the probability distribution, you basically know the conditional probability distribution of the random variable given a value of the other random variable. There is a problem, however, because if we would basically say what you didn't say it, but I can put it into your mouth. Ich kann es euch in den Mund legen. You said something like this. You didn't really say it because I didn't ask you in a way that you were able to say it. but so you definitely so the 0, that's fine. So the other one you didn't say, but one could think that this is the case. But there is a problem here. So does anyone see the problem if we just say the probability of y equals 1 given x equals 1 is 0/6 and so on for the other ones?
It doesn't sum up to 1.
Yeah, exactly. It doesn't sum up to 1. So we haven't defined a probability distribution over y in this case. Yeah. But we can do something to actually make these things here, so the 0/6 and 1/6 and 2/6 to sum, to make that sum to 1. And the trick is merely to divide it by the overall sum. So that's basically, you know that from Dreisatz in school, maybe. So if you basically you want, so if you think about the sum here, the sum is 3/6, obviously. So if you sum over these, you get 3/6, but you don't want the sum to be 3/6, so 1/2, but you want the sum to be 1. So what you can do is, for example, let's make that simpler than with these fractions. So if you have something like 2 and 3 and 1, maybe. So now you have the sum here is 6, but you want the sum to be 1. Then you can, of course, divide the whole thing by the sum. And then if you add 2/6 and 3/6 and 1/6, then you get 1. And exactly the same logic is used to now render these joint probabilities, to render them a conditional distribution. One divides each of these joint, which are actually here. So one divides each of these by the sum of them. Now the sum of them already has a name. It's called the marginal probability that x equals 1. Yeah. So we can, if we want to divide these by 3/6, we can likewise multiply them by 6/3. So that's something that you are familiar with from school. So, oops, Jesus, shouldn't teach all weekend, and I would be better on Monday. 6/3. So, and then we get 0, we get 1/3, and we get 2/3. Yeah. And if we now add these numbers up, 0, 1/3, and 2/3, we get 3/3, so we get 1. So we have normalized the values that we got from the joint distribution appropriately, so that now this thing here is a probability distribution over y. Yeah. And what have we done? Maybe to spell that out, what we actually did is that we looked at the joint probability of x being 1 and y being 1, and we divided that by the marginal probability of x being 1. And this is also what we did here. X equals 1, y equals 2, px 1 and px1 y equals 3 divided by px1. Yeah. So the point of this thing is that conditional probabilities are sometimes, especially if they are introduced with intuitive examples like this goat, or the probability that you get a male baby if the other sibling was male or something. That's all kind of confusing, or at least I always found that very confusing. So what is, from my perspective, relatively simple is to appreciate that once you define a probabilistic model, in this case a joint distribution, and it actually, you only get conditional probabilities if you have at least 2 random variables. That's also very important. So if you define a probabilistic model, a joint distribution over 2 random variables, so you define that, then the conditional probability distribution over one of the random variables given a fixed value of the other is already in the joint distribution. You just need to normalize it appropriately. And this is what is shown here. So one can write that a little bit more abstract. So one can summarize this as follows. What we did here is we computed a probability distribution over y given x, I think. That was the order, right? Yeah, y given x. And to do so, we put in all joint probabilities for our x value of interest. So we looked at the joint probability and we divided it by the marginal probability of x. Now, if you see such a statement here, this is how usually conditional probability then is defined. You should always in your head think that, okay, x can take on a number of values, y can take on a number of values. If you look at the marginal, x can take on the same values that it can take on in the joint distribution. And also here in the conditional distribution, py given x, x can take on multiple values, so 1 or 2, and y can take on multiple values. Yeah, so that's always important if you see these kind of very concise statements like this, that you appreciate that this means a probability distribution over y given a value of x, and x can take on different values. So you also have different conditional probability distributions over y here. So we computed 1 here for x being 1, but of course we could have also computed the probability distribution of over y given x equals 2, because that's also in the joint distribution. Yeah, so that's fairly important. And the whole thing, again, what this says just about this conditional probability distribution is the conditional probability distribution of y given x. That's essentially the joint distribution, but this joint distribution needs to be normalized. Yeah. Is everybody happy? No?
Could you just repeat the verbal description of that last part?
The verbal description of what? The last part?
The part that you have circled, it's a probability distribution of 1 over y.
So, okay, the part that I've circled, yeah, I can repeat that. So, so this thing here, that's the conditional probability of y given x. So the conditional probability distribution of the random variable y given the random variable x. The thing is, this is a very short notation for many conditional probabilities, namely the conditional probability that y equals 1, given that x equals 1, or the probability, the conditional probability that y equals 3, given that x equals 2, and all of these probabilities. All of these probabilities you can compute or calculate based on the definition of the joint distribution. Of course, that needs to be there. So if the joint distribution is not defined, you have no chance of computing a conditional probability distribution. But if it's there, and it's there because here we defined it, then to compute all these conditional probabilities, you just need to look up the joint distribution values and divide it by the corresponding marginal value. Yeah. So that's again something to do. So to exercise. That's actually also will be a question in the exam. Always has been. Based on some joint distribution, compute conditional probabilities and marginal probabilities. again, the whole point here is that you start from the definition of a joint distribution. If you're a little bit further, then and you have heard about Bayesian inference, then you might wonder where in Bayesian inference do I define a joint probability distribution. But you do, namely by multiplying what is called the prior distribution with what is called the likelihood. There you always define a joint distribution. Mathematically, the whole thing is more subtle. Maybe as a outlook, if you want to look into math books, because this thing here, so this ratio, of course, is only defined if the probability of x, so if the marginal probability of x is never 0. So we are lucky here because the marginal probabilities of x are 3/6 and 3/6. If one of them would be 0, then this thing wouldn't be defined. So this is why if you look in math books into conditional probability, it's gets much more complex because you need some definition that works always. So our definition actually only works if p of x, so the marginal probabilities for the random variable x are not 0. But we are not in math here, but in social, cognitive, and affective neuroscience. Good. So, of course, based on what we have done here, if we have a joint distribution, we can easily exchange the roles of y and x, and of course also compute the conditional probability of x given y based on the joint distribution. But we have to normalize differently. So with what do I have to normalize here?
Marginal distribution of y.
Yeah, very good. So that's just by exchanging essentially the letters. Yeah, again, the thing holds that if one of them is one of the marginal values is actually 0, then we have a problem. But that's fine for what we're doing here.
Why is it, sorry, why is the marginal distribution of y? Because, it's given that y, right? So
Yeah.
it's always when it's given of whatever variable, that's what the marginal is.
Exactly. So you can also, this is kind of, if you're starting to manipulate these conditional probability distributions, it's always, so what's behind this bar here, that's always in the denominator of this expression on the right. But here the inference was just, okay, y and x have been reversed. If you reverse y and x here, that doesn't really matter because it's a joint distribution. I always see my point here, but you don't see it. If you reverse x and y here, that doesn't matter because it's just the joint distribution. So the only thing that needs to change is what is in the denominator. Good. Any other questions about this right now? No. Good. Actually, with these definitions of conditional probabilities, it's quite simple to introduce Bayes theorem. So let's do that now. So we are now introducing Bayes theorem, which is a statement about conditional probability distributions. So maybe let's first write up again where we left off. Now, if we have two random variables, we can compute px given y by looking at the joint distribution and dividing by y. We can compute y x by looking at the joint distribution and dividing by x. Now, one can, of course, rearrange these equations. So if I multiply both sides of this expression here, if I multiply both of them by py, what do I get on the left side? Think back of school, like when you had something like this, and you multiplied both sides, for example, by 1/3. What happens? First this, So you multiply both sides by 1/3. What happens?
You isolate the x.
Yeah, but what do you write up next? You have done something like this, right? This is still school knowledge, or is everybody just tapping away on iPads in school these days and loading up videos on YouTube? Okay, so you multiply both of them by, so you do this. You've seen something like this, right? Yes, good. And then you get, like you said, you isolate the x and get this. Now, if you multiply both of these, now it's more abstract, of course, but it's still a symbol here. If you multiply both sides by p y, what do you get on the left side of the equation? Come on, anyone?
Is it still x? Or
yeah, you have to maybe look at the whole thing more in terms of maybe it's confusing because there are so many symbols. So think of the whole thing more as you have variables and they're called a, b, and c. Now, if you multiply the whole thing by c, what do you get on the left? AC, and here you get b. So if you now take this logic and treat px given y as a, px comma y, so the joint distribution as b, and py as c, what do you get on the left?
you get px given that y times py
Mm-hmm.
equals px. And how do you pronounce joint distribution?
Yeah, pxy. Yeah, so I think I usually say pxy because if it's the conditional, you say px given y. So pxy, I think that's fine. Good. And now we have clarified that. If we do the same thing here, but multiply with px, what do we get on the left?
X, pyx equals
Now py given x. Exactly. Good. So now what we actually found here is two expressions for our joint probability here. So we have pxy and pxy. So this is obviously, these are the same things. So we can write something like this: pxy equals pxy. I guess everybody agrees. And now we can put in this one and this one on each side, because we just found that this is equal. So we can do this. Yes. So now I basically just plugged in what we just did here, starting again from our definitions of the conditional probabilities. And now we can, for example, divide both sides by p over y. And what we get then is another expression for the conditional probability of x given y. So here we have now another expression of the probability distribution for x given a value of y, or all values of y essentially. We had this already. So it's nothing has really changed, that this entity is new. That entity was already what we developed earlier, but we now have a new expression for it. Yeah, we have now this expression here. And this expression here is called Bayes' theorem. Well, actually, the whole thing is called Bayes theorem, not only the right hand side. Again, I mean, you see quite easily that what is actually on top here is just the joint probability of x and y. The thing that comes with Bayes' theorem is some interpretation of these entities. So where do I put them? So maybe we delete this because you've seen it now. Get rid of this and focus on Bayes' theorem. So if things are then interpreted in terms of Bayesian inference, these kind of statements, the components of this kind of statements obtains a certain connotation. And often in this case, x is some unobserved random variable, and often a parameter, called a parameter, and y is often an observed random variable called data, and then the probability of x here, that's often referred to as the prior. But really, it's the marginal distribution of x in the joint distribution of x and y, like we did before. This is now just some additional nomenclature. This conditional probability of y, so of the data given parameter values, is often called likelihood. We will discuss likelihood much more in detail when we do maximum likelihood estimation. And this is sometimes called evidence, and don't ask me right now why this is called evidence. That's a long story in Bayesian inference. This is then called posterior. So if you ever have seen Bayes inference before, then I guess you've seen something like posterior equals prior times likelihood divided by the evidence. It's just an interpretation of actually a statement about conditional probabilities that we derived here in a few steps based on the definitions of conditional probabilities. So really what this whole thing is based on is just rewriting these statements. Then you get to something that is called Bayes theory here. What obviously Bayes theorem is not related to really is kind of interpretation of probabilities in terms of uncertainty versus frequentists. It's just something, large sample frequencies is just something that falls out of the probability calculus as we introduced it here, and you can interpret it from either an uncertainty quantification viewpoint or from a large sample limit viewpoint. It's Bayes theorem, but it's not actually that closely related to Bayesian inference. So we will not do much Bayesian inference, I think, in the winter term. If you are happy with everything that we're doing here and you're interested in looking at the GLM from a Bayesian inference perspective, actually we have a paper on that. Starke and Ostwald, making some blunt advertisement here. Starke Ostwald, 2017. You find that on our webpage. That looks at the GLM and fMRI, which has some special properties, which we will also discuss at one point, from a Bayesian perspective, and especially from a variational Bayesian and then standard Bayesian, strict and maximum likelihood, expectation maximization, and so on. That's if you feel like it's too boring what we're doing here, have a look at that. Good.
Understandable for us.
Everything is understandable.
Yeah, but human knowledge.
Well, if you feel so. So let's say not everything is understandable, but my writing is always understandable. It is. You just need to make sure that you have the correct previous knowledge that is required. Yeah, and that is hard to tell because I don't know what you know. But once that is the case, and then the writing is very understandable. Because it takes a lot of care. It's mathematical writing. It takes a lot of care in defining symbols rather than being a physicist and writing down some equations without explaining what the components of these equations mean. Good. I think that is actually a good point to take a break before we go into independent random variables. But are there more questions about Bayes' theorem at this point? Is any one of you preparing a paper that involves some Bayes in the other classes? No? What are you doing in the other classes? But I should stop the recording here.